we're saying that by the end of the decade, we're expecting like this 10,000 times increase in compute.
When Moore proposed this law in the 1960s, like, was it really obvious that that line would continue? It's been continuing ever since. The world is so complicated. There are all these, different forces at play. So how come all of these somehow average out into just a straight line?
We had dinner with a development economist, and we were telling him about, we think it's plausible that we could get a 10x increase in the growth rate, 30% per year. And then he responded, you mean 30% per decade? No, 30% per year. So we've been working on understanding trends in AI, and I'm curious what your kind of vision is for our work about these trends in AI.
So think about Moore's law. Moore's law is this empirical regularity that was observed about how performance in semiconductors was like increasing year after year. That was hugely influential in determining the direction of like technological fields. People were able to plan various years ahead of like this technologies existing because they had this expectation that GPUs or CPUs were going to get so much better. We're doing the same, but for AI, both on the input side and on the output side. We're mapping like this, the trend on like the resources that you need to develop these AI technologies, and also now trying to understand what this AI is going to be able to achieve in the future.
So I think we've had quite some success with the work we've done recently. I'm curious to go back and talk about how we started Epoch and what we were thinking when we started the organization. On the one hand, you had people very carefully studying what seemed to me fairly parochial questions in academia. On the other hand, you had people thinking about the very big picture, but doing it very not rigorously and very, by analogy, thinking about evolution or thinking about the human brain or just like what is possible in theory, maybe doing like a bunch of advanced math and trying to figure stuff out from there. But I totally kind of agree that the thing that I was really excited about was trying to do this very rigorously and carefully and actually looking at the existing research and try to see if we can extract information from there or build our own frameworks for kind of carefully thinking through these results. And some of the scaling law work I see as being really quite instrumental in building up this framework that we currently have for thinking about kind of advanced AI and development of AI.
So I think we should talk about what we mean by scaling laws. Maybe Ege, you want to take this one?
Sure. I mean, even going back to what you said, I think the idea people had about AI, maybe with a few exceptions, was heavily focused on software and coming up with better algorithms, better methods to try to match or exceed the performance of human brains. But if you make your focus algorithms, then it's actually quite difficult to argue that that's going to be a thing that's going to scale predictably or smoothly, or you're going to be able to say something about what AI is going to be capable of in 15 or 20 years. You would go and ask people, okay, so when are we going to get computer systems that can match the performance of humans in vision? When will computer systems be able to look at a scene and pick out what are the objects in this scene? And people didn't really have a good methodology for answering this question.
There were surveys and people asked researchers how much progress has been made and extrapolated that. But I think that felt really unsatisfactory.
Yes. And the precursor to this work was done by, I guess, maybe Moravec and Kurzweil. They were not rigorous by our current standards at all. I want to emphasize this. It was a very preliminary kind of work, but they were the only people, I think, who in the second half of the 20th century, let's say, were on the ball on this. And they said, it's not really so much about algorithms. It's about how much resources you have that you're putting into the algorithms. And the two important resources here are, the first one is how much computational power you're throwing at the problem. And the second one is how much data you're throwing at the problem. Initially, they were more focused on the computational power side. They pointed out, and Moravec has some early estimates, where he tries to look into how much computation the human visual cortex is doing. And the numbers he comes up with are so much larger than the computers which people had access to in the 1970s or 80s. So he made the point, well, it's not really that surprising that our performance is extremely underwhelming compared to what humans are capable of. We think a lot of what we do is very easy because it's just so intuitive. We just do it like that. But actually, the brain is a very sophisticated and advanced computer, and it hides a lot of this complexity from us. And Moravec predicted, based on Moore's law that you mentioned earlier, he just drew that line and he said, when are we going to get to a point when consumer hardware can actually match the amount of performance in the human visual cortex? He was just looking at the computational side of things. And he came up with a date of between 2010 and 2020.
Again, a straight line. Like, it feels like this is the recipe for success. You figure out like what is the straight line that matters, and you collect the data and just like extrapolate it.
I think the important thing here is that it is really kind of surprising, coming from a prior point of view, that the world turns out to be so regular that it is actually well described as straight lines. That's not at all obvious.
Yeah.
And like when Moore proposed this law in the 1960s, like was it really obvious that that line would continue at least until 2006, and depending on how you adjust it after that, it's been continuing ever since, right? Like that's actually quite a surprising thing, and I think people find it counterintuitive. The world is so complicated. There are all these, different forces at play. So how come like all of these somehow average out into just a straight line? I don't really have a good answer to this question, but the fact that it seems to happen so often, and it happens also in AI, is really what gives us most of our traction. And I think when people were thinking about AI in informal terms, well, you can't draw straight lines when you're thinking informally. You have to think quantitatively.
What are the lines when we think about it? Like, what's your bet for? Like, what are the most important lines that we ought to be tracking?
I mean, I think the one that we've been tracking from the start is really training compute, and training compute has been hugely influential for shaping the capabilities and both the depth and breadth of the capabilities of AI systems. We have some work where we try to decompose the sources of progress in the capabilities of LLMs, of vision models. And for those, we find that the majority, over 50% of the variation in performance is due to pure scaling pre-training compute. And then the other components are scaling and improving the data sets, improving architectures, improving algorithms, the implementations of those algorithms on hardware. So I think the most important for a long time has been pre-training compute. Now, I think the other trend that we've been tracking, actually we've been tracking this for at least 2 years now, is inference compute. There are scaling laws for the gains from inference compute, which kind of started out with the Andy Jones paper on the game of Hex. And once we saw that paper, we got pretty excited about the idea of scaling inference compute, not just for game playing systems, but more broadly. And we've been thinking about that as well as an important driver.
All right. So artificial intelligence is achieving more and more in recent years. We now have like AI that you can talk to, that can solve math problems for you, that can code for you. I think what we need to talk about is like, what has been driving this? What are the reasons why artificial intelligence has been getting better? What are the main highlights?
Yeah, so I think the key drivers have been the scaling up of compute, mostly in pre-training, but increasingly also for running inference. So we did this kind of inaugural project for Epoch where we tried to study the scaling of pre-training compute, and there we saw that since the start of the field of AI, about 1950, to roughly the kind of inception of the deep learning paradigm, we saw a scaling up of the pre-training compute, of the compute used to train these systems, at a rate that is roughly in line with Moore's law, so doubling every 18 months, 24 months or something. And since then, we saw an acceleration. So since the inception of deep learning, we saw this acceleration of training compute, increasing roughly 4 or 5 times per year. And this, we have found in kind of later work on language models and in vision models, has explained perhaps the majority of the performance improvements in both the kind of breadth of capabilities and depth of capabilities for vision and language models. The other important components have been algorithmic progress. So these are kind of innovations in architecture, the development of the transformer, for example, ideas about how to scale your compute, your model.
Could you include data quality also in algorithmic improvements?
Yep. So data quality has been a huge driver. Precisely how to quantify this or precisely how to classify this is a little unclear, because I think in large part this has been kind of ideas about how to generate, filter, what techniques you apply and bring to bear to producing a really great training data set. That you can think of as algorithmic kind of innovations.
Yeah, I feel like a bit derivative here. Like people have been talking for a bit about like, the three important things to think about when you think about AI is like compute, data, and algorithms. But I think it's right. And I think that what we have been able to do at Epoch is like actually rigorously show to which degree this is correct.
And you can go even more deeply into this breakdown and decompose pre-training compute into better chips, more spending on bigger clusters, longer training runs. And we've been kind of delving into this decomposition even more finely.
Okay, so there is like this four factors, right? There's like pre-training compute, inference compute, data, and algorithms. Like if I ask you to do right now a split of like which percentage of success of AI in recent years is due to like each of these components, how would you describe it?
Yeah, so I think, pre-training compute is probably close to 50% or something. And then the algorithms and data quality has been the remaining 50%. You can kind of break that down even more. I think in particular, data quality has been perhaps a really big part of everything that's not explained by scaling up the compute and the size of models and so on. So data quality has been very important. And the post-training kind of enhancement. So fine-tuning, supervised fine-tuning on instruction data, or fine-tuning and post-training on kind of very high-quality kind of coding or math problem examples, and making the model really great at solving problems of the sort that end users face when they want to use the model. I think that's been a pretty important component too.
Yeah, and chain of thought, which links into this notion of inference compute. If you let the model think for longer, they are able to solve more problems. This is now it feels like almost intuitive, but it feels like we're ahead of the curve in like having this notion internalized in the book.
Yeah, I think in our inference training compute trade-off report that we wrote, we made this claim that it seems likely to us that you can scale up the inference compute of large language models. And by the way, this was before people were rigorously doing this. I think this was round about the time that the chain of thought paper came out. We said that it seemed plausible or likely to us that you can scale up inference compute by 2 orders of magnitude and get the equivalent performance gain of scaling up your pre-training compute by say 1 order of magnitude. And I think, say, the release of O1 has really validated that point.
That's right.
I guess another thing I would point out is that the basic picture of compute data and algorithms, I think if you took that picture back to the 1980s or 90s, I don't think people would have really disagreed with you. And I think the important surprise, maybe, is that all the parts of this equation, maybe most importantly, the algorithms part, I think that was the part people really had serious doubts about, also basically turns out to grow smoothly and relatively predictably. This is not just the case in AI. I think it's a broader fact.
Just to clarify, you mean algorithms are getting better at like a very predictable rate?
Yes. You can imagine a world in which for 10 years there's very little algorithm progress. And then in 1 year, some team or some lab makes a critical discovery, and then suddenly models are 100 times more efficient. But actually the picture we see more is that algorithm progress is a very similar kind of pattern to Moore's law, where every year we see, say, halving or a little bit more than halving of compute requirements to reach a fixed level of performance. And I think if you pointed this out, like if you told this to people 20, 30 years ago, they would be quite surprised. Like this is not, I think, a result that they would have expected.
How convinced are we about the smoothness? I want to query your intuitions here.
Yeah, I think, we did some work about understanding the distribution of different innovations and, what is the, how kind of fat-tailed is this distribution? And, we did some work on, improvements in performance in, say, vision models and other models. And there we find that, there's this power law where, most of your innovations are driven by kind of smaller innovations that are kind of more kind of marginal. And then there are occasional, big insights that do push the field forwards. I think, averaging over like a year's worth of innovation each year gives you a fairly predictable or fairly regular gives you a fairly smooth curve. I think that seems basically right to me. So I would expect, within a factor of 2 or something, the slope being broadly accurate of the field of, if you average over all what all the top labs are doing, I think you can get within a factor of 2 of this kind of overall slope.
Okay, so I think one thing that obviously comes to mind here is that how do we reconcile this with the fact that AI architectures, the one that we know about that have been conducted at larger scale, like for example the one from Meta or like White Open, or the training process, are they're quite similar to like what was being done to train GPT-2, for example. Like how do we reconcile this with like us expecting like this smooth trend of improvements?
Well, I would say that architecture is just a very small part of what goes into even purely in software terms, what goes into a modern system. In fact, the fact that Meta and also many other people are willing to release the weights of their model, and of course also the architecture, because you need that to be able to interpret the weights, but they're not willing to share any information about, say, the details of their training process, things like how did they initialize their weights, which learning rate decay schedule did they use, where did they get their data from, they will sometimes say, we have trained on 15 trillion tokens. Okay, what are these tokens, where do they come from, how do you filter them? They just don't share this information. I think really a lot of the gains are hidden in these points. Another one is the development in the scaling law literature itself, which has shown that previously people were seriously undertraining their models, which means that they were giving the models way fewer data than the models actually could use to improve their performance. And this was essentially a suboptimal allocation, because you can use a greater compute budget to either have a bigger model or have more data. And the scaling law improvements help us better optimize this allocation. This was another substantial gain in efficiency. And none of those are really about the architecture you use. There are some minor improvements in architecture. Maybe you could say that the better embeddings that Meta uses are an improvement. Maybe you could say that grouped query attention is an improvement over the initial transformer published in 2017. But I think these are really fairly minor improvements. I think most of the gains are coming from the other factors that I mentioned.
I also think there's just a kind of a long tail of very many things. I think people like to say when's the next transformer gonna be invented, but I think this emphasis on just these small, big things, these kind of big, sexy breakthroughs, kind of belies the fact that many of these improvements are due to just very many small things. That would be my guess as to how we are making software progress.
I'm really very excited to track this better. I really think we should just do that.
Oh yeah, I agree. Tracking this better would be exciting. I do think though that if you just compare the architectures, there isn't enough small things that are different to explain the differences we see. There really has to be
something else.
Yeah, a lot of other things in the background, and I think there are.
So I think, and I believe you two will agree with me, that despite all the bottlenecks ahead, of the challenges ahead on getting the necessary power, getting the necessary GPUs, that we should be able to keep up with the rate of scaling we have had until the end of the decade. And that's 10,000 times more compute than what was used to train GPT-4. And that's a massive gap in performance. To put this into scale, like also GPT-4 was like 10,000 times more compute than what was used to train GPT-2. So like that same jump is like what we are by default expecting by the end of the decade.
How confident are you in this? So, specifically the claim that we'll be able to keep up this 4x per year that produces 10,000-fold increase in scale. Are you 50% sure? Are you more than that, less than that?
If there is the willingness to do it, I think I'm pretty confident that you can. So like the two biggest bottlenecks that we found is like, can you get enough power and can you get enough GPUs? And the power question is an important one, but that people already have identified as an important problem and that they're already working out solutions for. And there is precedent for like a large scales up of power production in the US and like in other economies. So like I think that people will just rise to a challenge. Like it might take like a bit of preparation and a lot of money, but they will be able to do that. With GPUs, it's a bit harder to scale since like GPU production is like so concentrated. But when we did like this investigation, like we roughly found out like, well, if TSMC keeps like expanding its production at like the rate that they have historically and the rate that they expect to expand in the future, like that should be enough to meet that demand. Is that right?
Yeah, that's right. So maybe let's get into the power component first. Yeah, so where are we? How much power do training runs currently use? And at what rate is this growing? And what is determining how much we should expect the energy needs to escalate?
So in order to train models of the class of GPT-4 or Llama 3, you will need between like 15 to 30 megawatts of power. Like to put this in context, like 30 megawatts of power is like not exactly, but roughly equal to the consumption of like 30,000 households in the US. Now, we're saying that by the end of the decade, we're expecting like this 10,000 times increase in compute. That doesn't exactly match with an increase in the amount of power that you need for training. There's like some mitigating factors, mainly that we expect hardware to be more power efficient in the future, and also that people will train for longer. So if you train for longer, you need like less immediate intake of energy at a single point. So when we combine all of that, roughly the picture that we expect, kind of like by default, this is like the default extrapolation with like trends continue, is that we should expect an increase in the power you use for training of like a factor of like 200, 250 or so. And that's still quite a lot.
By the end of this decade, 200.
By the end of the decade, like a 200 increase. So that puts you in the range of like, you're going to need for power, like, let's say like 5 to 15 gigawatts of power, which it's a lot. Like that's more than the output of like a single typical nuclear power plant. Though it is also not a lot in the sense of like if you look at like annual production of energy in the US, this will still be only like a small percentage. So now there's the question of like, well, will companies rise to the challenge? Will they be able to like expand data center capacity to the rate that is needed in order to keep up? And like what we did was like doing this very like basic extrapolation of just looking at like both historical rates of expansion of power in data centers, and also we looked at the plans of like the power providers. And even just taking this baseline, like it looks fairly reasonable to do training runs of the scale that will be on trend by the end of the decade.
So one constraint that is quite important here is that if you have a training run that happens within a single data center or within a single campus of, say, multiple data centers, but geographically together, then you have to kind of source that power from either a single grid or maybe a single power plant. And as you said, there are a few power plants that are of the scale to be able to power to be able to give you enough electricity to run 10 million GPUs or what have you. So we've been thinking about geographically distributed training, which enables you to tap into the energy infrastructure across the country in the US, which then enables you to pull together these very many distributed resources and power plants. And can you say more about how that might enable us to source the energy we need in order to kind of
That's right. So a 5 gigawatt data center, like my best guess is it's possible. And like there's definitely like some rumors going around of like people wanting to aim for that scale, but it's stretching it. Like there's like no precedent of like facilities that have like that level of power consumption. Like I think the biggest smelters on Earth like have a consumption of like 2 gigawatts or so. Distributed training is like this very appealing alternative if like they are not able to fulfill this dream of like giant 10 gigawatt scale data center, because then as you're saying, like, okay, I just have many data centers, each of them is drawing power from like a different source. Then that relaxes this constraint of like where you get your power significantly and makes it like so much more affordable and so much more easier to coordinate. But now like the question is like, okay, if you split your training across multiple data centers, like, can you do this? Like, what are the fundamental reasons you might not be able to do this? And like, I think there's like 2 main constraints that you need to consider here, which are like bandwidth and latency. Now, bandwidth is not really a constraint in the sense of like the solution, if you're lacking bandwidth between the data campuses, is like you just build more fiber optic, you just increase the bandwidth. And like the amount that right now people are spending on connecting data centers, like it's a small fraction of like what you spend on like the GPUs and the supporting hardware itself. Like to put this in context, like I believe that the fiber optic that goes through the Atlantic Ocean, at least one of them, like it costs like in the order of like $100 million to set up.
Yeah. So like, the idea here is then if you're spending like 100 or like 10 billion or 100 billion on your clusters, then what is a couple $100 million to like be able to connect these and actually orchestrate your training run. I think that seems to kind of match my sense that conditional on actually scaling this so far, the amount of resources that companies would be willing to expend are going to not be kind of a huge challenge or upset to their ambitions.
That's right. And then this other question is about like where latency is going to allow you to do the training, because the training, at least how we do it right now, is kind of like this sequential process in which like you process like a batch of data, then you update the model, and then like you use this updated model to process like a new batch of data. But here, like we just did the calculation for like, okay, what if we have data centers like in different coasts in the US? Like it seems like the latencies are manageable, so like they wouldn't stop scaling at least until the end of the decade on like current trends. But now power is not the only bottleneck, and in a sense, it's like the most malleable bottleneck. So really, I think that what we need to figure out is like, will we have enough GPUs? And what's your take here, Tamay?
Yeah. So again, if you think that AI is as powerful a force as we think and as valuable economically, then there should be a lot of effort going into relaxing this constraint and producing enough GPUs to power the training runs. So I think TSMC, if they receive enough advance orders and companies and these hyperscalers are able to convince and signal to TSMC that they're actually willing to pay for large scale-ups of their GPU production, then TSMC, I expect, will be kind of willing to expand its advanced packaging capacity to be able to turn the silicon into advanced data center GPUs. They're already kind of expanding this pretty rapidly. They're building new fabs for packaging to support this increased demand. I think there's been some foot dragging by TSMC where they're not fully convinced about the demand for data center GPUs. I think it's possible that these hyperscalers are able to like come together and actually commit to paying a bunch of money and placate and give confidence to TSMC that the scale ups that they could invest in are actually worth investing in. Mm. And if there's not enough convincing that happens very soon, then we might not produce enough GPUs. Okay. So I think the GPU bottleneck is indeed kind of a challenging one. I do expect, from what I'm hearing, from the rumors that OpenAI and Microsoft are working together on building these $100 billion data centers for doing training. That is very much precisely the thing that we would predict if this trend continues. And there are rumors that people are actually already planning for precisely this. And so I think this is quite plausible that it would in fact happen. But I do think there's some chance that that there isn't enough convincing through this chain of lab, hyperscaler to fab, that happens not quite at the right time for this to actually go through.
Yeah. So like to put this into perspective, like right now, if we put like all GPUs together on Earth, like what would you be able to train? Like a model of like 10 to the 28 flop or so,
Right.
something of that scale.
Yeah.
Like what you need is like that extra order of magnitude, that extra factor of 20 of GPUs to get to the scale that we need.
I think it's probably less than a factor of 20.
Mm-hmm.
So like currently you might, I don't know, there might be like 4 million H100 equivalents that are, scattered between labs so this is the production that TSMC has been able to achieve over the past couple of years. And so there may be a factor of 10 or something that they should scale this up. Unless you expect that there's going to be this massive consolidation of resources. If there's this massive consolidation, obviously they need to produce less, but I don't expect that to happen. I think there's going to be, this kind of distribution across some of the three hyperscalers.
Yeah.
And then there's also going to be some allocation between inference and training.
Okay.
I think like an order of magnitude scale up in production of TSMC is the thing that's needed. I think in order to do this, they need to scale up their packaging and some of the other kind of high bandwidth memory production. And they're, as you said, they're kind of on trend with doing that. So if you read their annual reports, they will say that they're scaling up at a rate of about 30 to 60% per year, which would get you precisely the kind of order of magnitude increase by end of decade.
So we're going to have enough GPUs. We're going to have enough energy. I guess like the other question that always people ask us is like, are we going to have enough data? Are you going to be able to train the models?
So we've chatted about power and GPU production, and then there's the data wall that people are often talking about. There's Sam Altman tweeting, tear down this data wall or whatever. We've been doing a bunch of thinking on this question, and we've done some of the early work that we've been continually updating to contribute to this picture of where data is. So Jaime, is this data wall real? Are we going to hit this data wall anytime soon?
So let's go back to the basics. Like where are the companies getting the data that they're training on? They're getting it from the internet. How much data do they need in order to train things like Llama 3? I think they were training on the order of like 10 to 20 trillion words of content, which is a lot, but this is still only a fraction of what exists out there in the internet. Now, not everything that's out there in the internet is going to be good for you. Some of that content is just like very low quality, and you're not going to be able to train on this. Like perhaps a way of thinking about like how much more data are we going to have out there is like, primarily, I expect that a lot of this data comes from like efforts like Common Crawl that go through the internet, gather like a bunch of data, make it create like an index that's like easy to crawl and like filter for quality. And Common Crawl, our best estimate is that it only encompasses like a fifth of the internet or so. So like in theory, like if you did like more exhaustive crawling, like you should be able to get like 5 times more data, even if you still apply like the quality filters that you want to make sure that you end up with data that is of high quality. And there is like another wrinkle here, which is that at the moment, like the state of the art on training is like you train once on each data point because you're not data limited, right? So like it's better to just train on like a more diverse data set. But once you get to the point where like you are really struggling to get more data, then what you might do is just like train a few times on each data point during pre-training.
I think some of the labs are already starting to train multiple epochs. Especially on the very high quality stuff. there's been this research on multi-epoch training, and there, the picture is that you can train basically up to something like 10 epochs before you really start facing the diminishing returns of seeing the same data over and over again. Before then, it's as if you have a fresh data set. So you can multiply by a factor of, I don't know, 4 or something relative to maybe the 2 epoch training that people are doing right now. And that gives you already a factor of 4 of like the effective data set size. And then maybe you can train for even another factor of 2 and still get some gains from that compute spend.
Yeah, and take into account that the amount of compute that you use scales with like the square of like the amount of data that you have. So like you don't need that much more data in order to get to like that 10,000 times larger model than GPT-4 in terms of compute. You just need like 100 times more data. You might be able with text to like almost get there, but you might struggle a little. So like right now what we were saying is that, okay, you might get like 4 or 5 times more data from just scrapping more exhaustively the internet, and also like 4 or 5 times more data from training multiple times on each point. But that's in total like a 25x increase. And how do we get to the 100x increase? Like right now, I think we have like 2 main hypotheses of what you do here. Like one of them is like you start training on modalities other than text, and the other one is like you train on synthetic data.
Yeah, and multimodal training is just very useful. So you have OpenAI and others exploring multiple modalities for inputs and outputs, and I think like they're finding a bunch of interesting use cases. I expect that those use cases will be sufficiently valuable to fold in a bunch of image, video, audio into the training data.
Yeah, just think about the cloud web browsing stuff. Like the web browsing stuff right now, one of the reasons why I think it's not very good is because it doesn't quite parse the screenshots that it's being given.
Mm-hmm. And the web browsing stuff you're referring to, like taking control over the user's computer.
That's right.
And then performing some tasks like, I don't know, troubleshooting your computer if you have an error message or something like that.
That's right. So multimodal training, it seems, I agree, like it's gonna be like hugely useful. It's something that the companies will want to do, and I think it might be reasonable to expect that if you train on other modalities, also your model is gonna get better. Like here, like the evidence is like a bit sketchier, but like I don't know, it seems intuitively reasonable that by watching videos of like people dropping objects and such, you might learn about like physics, and you might learn about like how the world works in a way that you cannot from just like reading text. I'm not like super convinced by that, but like I could see it as like something that ends up working for this scaling. But then there's the other question here, which is synthetic data.
Yeah, so synthetic data, people are definitely quite bullish on it, at least for specific capabilities. So,
I am.
right. So, getting really good at writing good code, or solving math problems, or tool use. So, kind of having the model generate a bunch of instances of like good reasoning or good application of various techniques, and then training the model on this on this data set. I think people are using this quite a lot already, and there might be kind of a more general sense in which you can use synthetic data to build these very basic representations, just like pre-training does with in the normal data set that you get from the internet.
Yeah, so here's how I think about synthetic data, and that makes me very bullish on like this strategy overall. Like we know that it's possible to distill models. Like it is possible to take a model that is like quite large, that has been trained on like a bunch of data, make it produce data, and then you train like a slightly smaller model that like it's trained on like the outputs of like this model, and it learns to like at least resemble the outputs of like the larger model. And then like on the other hand, you have like this inference scaling, where like if you let models think for longer, they produce like higher quality stuff. So like this immediately creates like these this suggests this feedback loop, right? Where like you get the models at the frontier, you use them to generate synthetic data, taking as long as they want. Like you use them, you generate like 100 answers for each like digital prompt, and then like another model sifts to find like the highest quality answer that it has produced. Or like even better, in something like math, you check like is this solution like actually correct? And you use that higher quality data set as like the basis for your training. And this is what allows you to train for longer.
Yep. So there's this general principle that often verification is easier than generation.
Yeah.
And this is especially true for math, for programming, say, where you can do unit tests. And then you can generate a bunch of candidate examples and then use this verification, or you check the quality and you filter out the low quality stuff and use the very high quality examples as training data. And so this suggests a way of spending compute and turning compute into data. And so if you're going to be data constrained, but you have enough compute, then this suggests that you can balance those by just using your compute and translating that into more examples to train on.
That's right. We know that this is already happening for post-training. Like Meta was like quite transparent. Like we train one version of our model on code data, and then we use it to generate synthetic examples of like more core data that we could continue training on. Like I think here is like, is this going to be useful also for pre-training? But I think that yes, and I kind of suspect that already within like OpenAI and these large labs, that there's already like a fraction of their compute that's like a non-negligible fraction being dedicated to generate synthetic data.
Yeah, like synthetic data is already feeding into pre-training data just by virtue of a bunch of AI's output, ending up on the internet, and they're producing, OpenAI is producing like 10 or 100 billion words per year that ends up on the internet.
I guess I would raise like one concern here, which is that if synthetic data only allows you to match the quality of the existing high quality data distribution, then you have this problem that generating a lot of synthetic data, like usually training on a single token takes about 3 times as much compute as generating a single token. But if you want to get high quality synthetic data, you're going to have to generate a lot of tokens for each token that actually ends up in the training data set. And that's going to mean that actually most of your compute is going to be spent on generating the data and not training on it. In fact, this is what has happened with past approaches that train the model basically on synthetic data. Maybe the biggest one is the line of work that came out of AlphaGo, where it took about 100 times as much compute to generate the data that the models were later trained on. But yes, so this might be a problem. But on the other hand, I think there's a reason to expect synthetic data to be much higher quality than data you just find randomly on the internet, even if you have filtered that data for quality. And I think one reason is, if you think about how humans learn to do tasks, there are some tasks that some things you can learn just by reading or watching like other people's like text or actions or whatever. But actually for a lot of more complex tasks, for instance, if you want to be a good chess player, if you want to be a good Go player, if you want to be a good programmer, you can name a lot of other things of this nature. It's not really enough to watch other people do the task, even if you like do that a lot. But if you practice yourself, you get a lot more gain out of that data, it seems, than you just get from watching other people. So there's a hope here that synthetic data ends up like just per bit or per token or whatever being much more valuable. And therefore you actually don't have to generate anywhere near as much as we currently do for pre-training. And so we can still make it to this like deadline by the end of the decade. We can keep up the scaling, which I think might be difficult if you have to rely on synthetic data that's just about the same quality as the existing data distribution.
Yeah, I think this makes sense to me. So this is the reason why I'm personally bullish about synthetic data. And this is kind of like this is the out, right? If you run out of natural data, this is how I will envision that the companies are going to keep up with scaling the models.
Yeah, of course. I mean, there are even some examples of, so for instance, DeepMind recently announced this result that they were able to get very close to gold medal performance on the IMO. And that was a combination of 2 systems both of which were trained on synthetic data. There was a model that just solved geometry problems, another model that did formal proofs, and they don't give like a lot of details about their approach, but they say they basically used something similar to the AlphaGo approach, which means some pre-training on human data or existing proofs. In the case of the Go approach, before in the first version of AlphaGo, they had pre-training, what we would call pre-training, on just human games. That got the model up to something like decently strong amateur level, but far below the level of professional players, masters. And then starting from that base, you were able to do self-play, generate synthetic data. Exactly as you said, you have this ability to spend more inference compute, generate more high-quality data, and then train on that data. And they were able to improve their model's performance by using this method. And I think they used the exact same approach in formal proofs, which I think it's actually difficult to imagine that line of work succeeding just by pre-training. I think probably that would not have worked even if they had a lot more resources. So synthetic data is really vital for improving capabilities in some domains. I think you can get gains from it that you couldn't get from pre-training even if you scaled up by 100 or 1,000x.
So Ege, you've recently been thinking a lot about whether there are any limits imposed by, say, the latency of doing training, or by GPU failure rates or other things that become issues as you scale up your cluster, the number of participating GPUs in training by an order of magnitude or two or more, as this picture suggests we will if this trend continues. So I wonder if you could say more about what you've been thinking about and what your conclusions of that work have been.
Yeah, sure. So the basic way I would try to explain this limit to someone who's just not familiar with any of the details is we currently training runs of frontier models take about 3 to 4 months. We think, as Jaime has explained before, that this might increase, but not by a huge amount. So maybe it will go up to 6 months, or maybe speculatively up to a year. But probably not much more than that. We don't have.
Can you say more about why?
Sure. So one thing is, if you want to make it to the end of the decade, then we don't have that much time. So that's one, like we can't scale up by that much. But I don't even expect us to get close to that limit because, first of all, the fact that we have these algorithmic innovations means that if you start like imagine that someone started a training run in 2019, which was just finishing about now. Like even if they had spent a lot of compute, that model would just have been not very useful by now. It would be way, way below state of the art. So that means you're incentivized to not really do training runs that are that long.
It's like this question of how do you optimally colonize the galaxy? Or like you want to like wait on Earth until your technology improves, and your rockets are really fast. But so you don't want to launch very early with a very slow rocket because that's going to be overtaken by a launch much later with a much faster rocket.
Yeah, I think that's a very good way of picturing this, actually. But whatever the reasons, let's say that there is some kind of time limits that we have to work with. We have to do a training run, say, in less than 6 months. Then the problem you face is that as you scale up your training run, so the way training works is that you start from some random points in parameter space. The model is basically giving you random outputs. And then you gradually adjust the model step by step to better predict your data, let's say, in the case of pre-training. And each of those steps you have to do in sequence. You have to take the first step before you can take the second step. You can't take them at the same time. You can try to just pack more punch into each step. You can try to go further, but there are limits to how much we can do that. That is controlled by just how much information you see when you take each step. But at some point, you just have seen enough tokens, enough information, and just seeing more doesn't get you further. So there's some limit to how useful each step can be, which means you really have to take some number of sequential steps. And this number, we think, increases as you are training bigger models on more GPUs. The implication is that if your entire time is fixed, but you have to take more steps, then each step has to take a shorter amount of time. And you can imagine that if we push this out by, 10,000 times, 100,000 times to make it, to keep this trend going by the end of the decade, then we're going to really end up with individual steps that take a very short amount of time. And a lot of things that people today don't think of as problems at all, like latency of communication between different GPUs. Today, it doesn't matter at all. We're like so far from this being an issue, maybe by a factor of 100 or 1,000. But well, if you scale by 10,000x, 100,000x, these things that people currently ignore can suddenly become issues. And we try to work out in our recent paper that I was one of the co-authors together with a collaborator, we try to work out when these limits would kick in if we look at current technology and also what kind of improvements can we expect assuming some reasonable technology improvements by the end of the decade. We end up with the bottom line that I think there's no obstacle to keeping the scaling until the end of the decade. But if you try to go further, then I think we start having problems on the current trajectory. Maybe we can do like over GPT-4, we can get something like 10,000 or 100,000 like scale up. Probably 10,000 is more realistic before we start to see substantial decline in the efficiency with which we use GPUs. What happens is GPUs currently spend most of their time just doing the computations that are useful for your training run. But once you get to the scale, other things like time taken for communications start dominating. Like it just becomes harder and harder to coordinate these things because each step has to be done in such a short amount of time. And at that point, the efficiency with which you're using your GPUs start declining. But I don't think this is an issue to make it to the end of the decade. And also, I think even after that, there are methods to do what I said before, which is to pack more punch into each step so that you get more value out of it, so you have to do less steps. One of the approaches that I think historically has not been promising is, people have talked a lot in the past about why do we, like the way we train these big models is we just do a very local computation of which direction should I go in to like better fit my data. And then you just take a step and another step, another step. And people have said, well, the amount of information we're using in these steps is really pretty limited. We can be a lot more sophisticated. And in fact, when people do simpler optimization problems, ironically, they actually use more complicated optimization methods than what we use in deep learning.
Like second derivatives or something like this.
Exactly. But the reason these methods have not worked, it's not that they don't pack as much punch per step. They do. They're better in that respect. But the problem is they're much more expensive. And when you work out like how much extra value you get per step versus how much more expensive each step becomes, it's just not worth it to use them. So they have not been competitive, but they would be an option if ever the current optimizers hit a limit, which maybe after this decade.
So summarizing, I think what I take away from here is like these bottlenecks, these like data movement bottlenecks, like they are like an important problem to solve. But like once you have them in your radar, and I fully expect that the companies like will already be thinking about them, even before we wrote that paper, like they will be able to solve them.
I think, yeah. So one thing I really like is that we're like identifying these novel kind of issues that have not been on the radar of much of the AI community outside of the labs.
Yeah.
Within the labs, I'm sure they have a bunch of research where, we're basically replicating things that they've already known for some time. But otherwise, without our efforts, I think some of these ideas would have taken much longer to be uncovered for these like key strategic or conceptual questions and considerations to be uncovered. And that's like one thing I'm really excited about with our work.
Yeah, me too.
So, you mentioned, latency, which is, largely a kind of hardware property, right? And in terms of solutions, you've been thinking about much of the software side of packing more punch in each step. So you expect the bottleneck, the way that we end up overcoming this bottleneck, if we do, to be more on the software side.
Yes, I think the reason for this is we have examined the historical improvements in the kind of latency that we would care about. And it has been fairly slow. So for instance, the
DRAM access latency has increased by a factor by 30% over the past 2 decades or something.
Yeah, it's very slow. It's the same thing is true for like there are some operations that you need to do during distributed training to make sure all your GPUs know about what each other are doing. And those operations have also been like, it's about the communication latency between the GPUs. That's also not been scaling very much. We've been seeing much more scaling in flop per second and also in bandwidth, but not so much in latency, which means when you plot like what's been happening to this latency limit, it sort of looks like it's flat. Yeah. And that's, however powerful your processors are, if you have this serial, like you need to take so many steps bottleneck, then at some point it doesn't help very much at all. I think another reason to be more optimistic is that, yeah, people aren't currently optimizing this very much, but that's because you might argue that it doesn't matter. So there hasn't been much optimization pressure applied to this problem. Even there, I'm a little bit skeptical for the reason that I agree the latency bottlenecks are basically non-existent right now at the current scales and training, but that is not really true in inference. Yeah. So if people were able to reduce latency, that would actually have a meaningful impact on inference economics, which does give a strong incentive to do it. Right now, we estimate that the amount of compute the labs are spending on inference is not very much different from the same order of magnitude as they're spending on training. So there are big gains to be had there. But despite this, the GPU producers seem to be unable to really get these latency numbers down by very much.
Yeah, I think I find that quite persuasive. Like, I also think of latency as like the reason why you cannot just scale up to infinity, at least with the current setup and way that it works. It is still beyond like what is on trend yes. by the end of the decade. So you're gonna still get till the end of the decade. But like, if you were trying to think of like how do we schedule a training run that is like uses a million a million times more compute than what's expected by the end of the decade, like you're gonna run into
the laws of physics will eventually
get you.
Yeah.
Kick in.
Yes.
So another constraint that people sometimes ask is if you have if you have 10 million, 100 million GPUs in your cluster, these have rates at which they fail. So they fail maybe every 10,000 GPU hours. There's some kind of erosion or some kind of issue with the hardware, some flaw in manufacturing that results in the GPU giving out and shutting down or whatever. So we've been recently thinking about whether this is an issue, and I was wondering, Ege, if you could summarize whether or not this ends up being a constraint for scaling.
Yeah. The short answer is that it doesn't end up being a constraint. Even with present methods that people use so what you have to do to deal with a failure is ideally you need to have an automated process whereby if a particular GPU, or sometimes it's the CPU or the power supply unit or whatever in a particular machine that has failed, you want to just automatically swap out that machine, replace it with a machine that's functioning properly, and keep your training run going. When you're at really small scales, like say below 1,000 GPUs, then the failure rates are manageable enough that often people didn't even invest in automated recovery from failures. What they would do is when something failed, someone would just be on duty and they would just handle it. I've heard stories, I'm not going to say who has told me this, but in some of Google's earlier training runs, they would have like people literally inside the data center just running around and replacing faulty interconnects that has failed. They would swap them out by hand. Okay, that works when you're at a small enough scale, but at a big enough scale, you really want something automated. You don't want to deal with this problem. To give some idea of how frequently these failures happen, the recent Llama 3.1 paper from Meta, they give data about how many failures they experience throughout their training run. We know how much compute and how many GPUs, what the hardware setup was. So our estimate is something like one failure every 50,000 GPU hours. This means that if you have 50,000 GPUs in your cluster, which is a little bit more than what they had, you're getting one failure per hour. So one day you get like 24 failures. That's actually a lot if you have to recover by hand. But Meta had an automated recovery mechanism. Their idea was, suppose that some GPU has failed, we need to restart it. If you restart it, we lose the information on that GPU. So we just periodically save the information we need to some remote storage. When a GPU has failed, we just start and recover it and keep our training run going, right? And you can try to examine when would this become an issue? Well, you can sort of think intuitively that the point at which you start having a problem is when the time between consecutive failures becomes smaller than the amount of time you need to save and recover from this remote storage. But when you work out how much this will be, and even for their model, you get to a number like 70 million GPUs. So it's a lot. It's like that is already enough to make it to the end of the decade. And then there are much more, like, first of all, the fact that you will be scaling your model up gives you an advantage. The fact that there are actually more sophisticated ways you can recover from failures. For example, instead of saving to a remote storage, which is going to have fairly limited bandwidth, you can say you have some number of GPUs in your training run. Each GPU can send its state to, say, 3 or 4 other GPUs in the cluster. And then you have like 3 or 4 backups for everything in your cluster. When you work out the mathematics of this, you see that if you have like 4 backups of each GPU in like random places in your cluster, then it's extremely unlikely that all of those are going to fail at the same time. So you will always
uncorrelated,
yes,
then
if
the
it's
chances
uncorrelated,
are extremely low.
That's right. So and that gives you much more bandwidth because you already need this very high bandwidth interconnect between your GPUs in your cluster and between nodes to even facilitate your training run, setting aside checkpointing. You just need this high bandwidth of communication. Well, if you already have it and it's already there, then why not use it for checkpointing? It's a very simple idea. And when we try to estimate, okay, like how big could you make training runs with this kind of strategy, you get like, even with very pessimistic assumptions about how your bandwidth might decline, bandwidth per GPU might decline as you scale your cluster, you still get like 10 billion GPUs or more. So this is not going to be a problem. I think like in anything else is like more likely to bottleneck scaling than GPU failures.
Nice. It's going to take a lot of engineering work to like orchestrate such a training run. And
yes.
Maybe you'll have robots instead of humans running around solving out interconnects. And there's going to be progress that we'll have to make in order to orchestrate training runs of this size. But it seems like there's no kind of, in principle, reason to expect that.
Yeah, there's no fundamental barrier.
Yeah, there's no fundamental barrier.
I think that distinction is very important because like, I wouldn't say that, oh, it's just going to be very easy to like scale. You're just going to have to buy the GPUs. Like in practice, each order of magnitude of scaling poses a bunch of engineering challenges. But I think like the way we look at this is imagine that you're spending $10 billion on the hardware in your cluster. With $10 billion, you can pay for a lot of engineering time. So if it's something you can solve just by having a lot of engineers thinking about the problem, then for us, like it's not really a significant bottleneck. We care about things that you cannot just overcome by spending a small fraction of your budgets on engineering or GPU cooling or this or that. Like these are things that just add small constant factors on top of the cost.
Well, that small cost factor might be like 100 million, to be clear.
Sure.
But it's still like small compared to the overall cost.
Yes.
So our kind of worldview is that AI is going to be kind of so economically valuable and capable of kind of maybe accelerating growth and certainly producing a bunch of output, so that these kind of costs, while large, end up being fairly small relative to the upside of that AI will likely deliver.
Let's talk more about this. Like we are talking about like, okay, if people want to build like these models using 10,000 times more compute than GPT-4, we think it's going to be possible by the end of the decade. But what does this buy us? Like, what do we expect to see from AI in coming years?
And why would people do it? Like, I think really this is the important thing. Like when you look at what's going to limit scaling, yeah, there are like energy and chip production and so on. You can see some limits there, but really the most decisive limit, the limit that could be most decisive is people just don't want to spend the money, because we are talking about by the end of the decade, if you want to keep this up, on the order of like $10 to $100 billion being spent on just one training run. And then imagine that across many labs and imagine all the experimental and inference compute that has to go along with that. You end up with fairly large budgets. So what is this going to get you, right?
And that's the amortized cost of like a single training run. So just the cost of the cluster is going to be in the hundreds of billions of dollars. All right, so we expect that artificial intelligence is going to keep increasing at a very fast pace. The natural question to ask here is like, why will people pay for it? Like the scale of the investment that's going to be needed to build a cluster where you can train a model that is like 10,000 times larger than GPT-4 by the end of the decade is going to be on the order of like hundreds of billions of dollars. Like, why would people do that? What do you expect AI to be able to do, and what impact do you expect it to have in order to justify such a large investment?
Yeah. So I think one fact that's quite useful to keep in mind is just the amount of money that's spent on wages each year, right? So about, wages or human labor is the most valuable factor input in the economy today. About, 60, 70% of total income gets spent on the wage bill globally. So this is, like $70 trillion a year. So if you're able to fully automate human labor, you can capture this enormous sum. And this is a flow rather than kind of a stock. And so that's extremely valuable if you do a simple discounted cash flow model of tens of trillions of dollars a year. Capturing even a fraction of that is worth investing hundreds, if not trillions of dollars per year on trying to capture.
There was a recent comment by Masayoshi Son that he was being asked about like the current rate of investment into AI, and he said, well, if you can automate even like some of the economy, then imagine like how much that's worth trillions of dollars, and that's per year. As Tamay said, it's a flow. So he was saying, the current rate of investment is even like too low, right? We should expect it to go up over time. So.
And I think that's basically our view. It's kind of funny that we have this agreement with Masayoshi-san, which otherwise I don't agree much with. But we have the same kind of view that the current rate of investment is just much too low relative to the economic value and the potential that AI holds. And I think it makes sense to spend a lot on kind of building out our infrastructure for being able to do this kind of training and running inference well in advance of when AI is able to do full automation or even partial automation. I think the reason for that is just that it takes time to build up the relevant capital, the infrastructure, to run and serve models. So things like energy, power plants, fabs, all those take time to build. And investors don't want to be caught out of the blue, that suddenly you have a very capable model and the value of GPUs skyrockets, and basically that the infrastructure isn't there to support this kind of the serving of this model or the training of this model if we have innovations in software. And so it'll make sense to kind of well in advance spend much more than we're currently spending in advance of actually doing substantial automation.
So how far are we from this? Like, do you think that by the end of the decade, we will already have full automation?
Yeah, I think by the end of decade is probably too soon. I think, so we're projecting, this 10,000-fold scale up. And I think this is like kind of a long way towards this kind of idea of having a drop-in remote worker, which is, this idea that you could have an AI system take control of your computer or kind of use a computer to accomplish the types of tasks that remote workers would do. So troubleshoot your computer, remotely log in and figure out what's causing this issue and try to identify and resolve it, or do a bunch of other types of work in IT or finance or accounting and other things that can be done kind of remotely. And existing estimates of jobs that could be done remotely are on the order of 50% of the economy. Notably, this has increased since COVID. Like before, economists thought that work needs to be done in person, and this is one of the explanations for why there are cities of the scale that we see today. That some work needs to be done remotely. I think COVID has kind of poked holes in this kind of idea that the majority of work needs to be done remotely. Some work
in person.
In person, yeah, that's right. So I think close to 50% of things can be automated with remote drop-in remote workers.
Yeah, like a big challenge that I foresee here is like you're gonna need to build infrastructure to be able to accommodate these AI workers. And it seems that once it became clear that you needed to work remotely during the pandemic, like we were very quick in building this infrastructure. So now a bit of the lesson is like, well, we will get better at building that infrastructure pretty quick. Like in the same way that like we improved quite quickly, like technologies for video calls and like communication with your workers when it was needed, like we might be able to find workarounds or like finding ways of like integrating AI into the economy in like a more seamless way. One thing that's important to reflect about is like how fast and sudden this change can be. Like I will imagine like even if we have like AI that already can solve like very complex like math problems, like that doesn't mean like immediately that the world is gonna like speed up by 100-fold. Like what do you envision like the process is gonna be like from like we have this AI that can solve like pretty much like any task that a human can do to like this AI like having like a large impact on the economy?
Are you like referring to just cognitive labor or also embodied tasks?
Cognitively at this point.
Yeah.
Sure. I think like a simple estimate would be you just get a lot of AI workers on the tasks that we can currently do remotely. As Tamay said, let's say 50%. I think that's a reasonable order of magnitude type estimate. Then you could at least get a lot of value out of those tasks, insofar as you think like the bottlenecks in the world economy are not very strong. And maybe insofar as you think the people who are currently doing those tasks can, over some period of time, acquire new skills and move to the jobs that AIs are not yet able to do, then we should expect, like that could double GDP, or global domestic product or more, right? So just because you automate half of tasks, all those people move to tasks you have not automated yet, that could already give a doubling and probably more than doubling. But now how quickly does that happen? I think people disagree about this quite a bit. Even inside Epoch, there are a variety of different views. Some people think it's plausible that we would get the system that is basically a drop-in remote worker. It's like as cheaper than a human. And maybe some people think 10, 15 years. I think like longer than that. So I would not expect over, say, the next decade, but the next 10 years, so not just by the end of this decade, to see like a very dramatic acceleration in growth. Maybe we would see like a few percentage points increase on the average or something like that. So not like very exciting, but if you look at the historical trend, growth in advanced economies has been declining. So even stopping that trend and like starting to increase that again would actually be a major change. So it'd be a big deal in the world of economics. But as maybe we'll see later, it's actually kind of small compared to the changes we expect to happen later. So
let's dive a bit more into this, because what I think we believe is that for any single task that we can think of, for any single benchmark, for example, that we can think of, like we sort of expect like the AI is going to make like great strides there. Like even for like, we did recently like this very hard math benchmark. Even for that one, it seems like the median expectation at Epoch is that by the end of the decade, AI will already be able to solve like many of these like complex research level questions. But there's this gap between like that and then like this picture painting to like, oh, there might be like a long tail of tasks, or like there might be like a long tail of challenges to overcome before it gets distributed in the economy. Like what is the distinction? Like why?
I mean, I think part of this is just it's been historically very hard to capture in benchmarks the types of tasks that people are doing in the economy.
Mm-hmm.
And I think having a benchmark that is able to capture this very well is just extremely hard. And so I think it's natural to think that benchmark progress is going to just be much faster. Like key reasons you might point to is the time scale over which such a task is performed. Mm-hmm. So often benchmarks, you need to do some reasoning, but you can do that reasoning within, maybe an hour or something for our very hard frontier math, say, where humans would take maybe hours to solve. And so this is longer time scale than many of the traditional benchmarks, but still not the time scale over which kind of key economic tasks are performed, which might be weeks or months or what have you. And I think that ability for a model to be able to execute plans over very long time scales is a component that I expect to take slightly longer than solving these types of benchmarks, even the ones that are very hard.
I would point to a different phenomenon, which is that there's this paradox in AI called Moravec's paradox, which is that the tasks that a computer or an AI finds difficult are not necessarily the tasks that humans find difficult. And Moravec's explanation for this was it's because the tasks humans find difficult are tasks that we have only started doing recently in evolutionary history. And the tasks we find easy are tasks we have, maybe not just us, but like even lots of other species have done for hundreds of millions of years or maybe longer. Those tasks are much more optimized.
So like the first case would be, the first class of things would be things like math and programming and chess or Go. And then the other tasks that we've been doing for a very long time in our evolutionary history is walking and fine motor skills and things like this.
That's right. And I think to some extent even, like for instance, language is now basically something that AIs can do. And well, if you look at the evolutionary history of language, it's actually not that old of a skill. Like most humans are really the only species we know that have language. While if you look at the ability for locomotion and things like that, so many species have that skill. Like even bees and whatever can do it in their own capacity. And we can't even match that yet. Like bees have very small brains actually compared to humans. So you might have expected that, yeah, like maybe we haven't yet trained models that could be on par with the human brain. But like, is it really so hard to be like even on par with the brain of a bee? I think it's interesting the extent to which the progress has been so lopsided towards some tasks, and the progress in robotics in any form, not necessarily in a human envelope, but even like something that could control the body of a bee, has been very, very slow. I think it has been very disappointing. I think the reason for that is probably this argument that those capabilities are just much more efficiently implemented. And our methods, so right now, are quite sample inefficient. This is a difference that's very easy to see. If you train an AI to play Go or chess or whatever, yeah, they can play it at a superhuman level, but they can only do that after playing millions or tens of millions of games. Yeah. And well, how many games can a human even play in their entire life? It's not that many. And a human can get to a pretty good level of competence on this kind of task, even with a few hundred games, which is extremely difficult for AI systems. So there's this big gap in efficiency. We don't know where this comes from. And I think that like these kinds of things where biology is very efficient at doing some things that are very old are just forming a huge chasm. Like I can't even think of really prominent benchmarks that try to probe at capabilities that are very old in humans.
I think I kind of agree that Moravec's paradox applies to things like robotics, and I think that's a very compelling example. But for remote workers, I'm curious what types of tasks or what types of capabilities or competencies are really hard for AI systems to match human performance.
Yeah, so right now I would say return to the same point about sample efficiency. So the one way I would express this is it's very normal when a company hires a new worker right now, especially if it's like a fairly junior hire, for them to be quite unproductive for the first few months that they're at the company. That's like essentially like a training period in which they learn the context that they're supposed to be working on. They pick up some skills that they didn't have before, and they have to do that with like a fairly limited number of samples compared to what we show AIs. If you try right now to get an AI to adapt to your specific context, it's actually fairly challenging. Like there are two approaches right now we have. One is fine-tuning. The other is sort of in-context learning. Fine-tuning, you need less data than in pre-training, but still way, way more than typically you're going to have access to in this kind of setting. And in-context learning is like much worse than we see in humans. For instance, in math problems, when we were talking with some mathematicians as part of our benchmarking project, they mentioned that when they try to get current models to solve a math problem, sometimes if the problem is easy, they solve it, and that's great. But sometimes they try an approach that doesn't work. And then the human user says, oh, like what you did, it doesn't work. Like try something else. And often they will sort of go through the motions of trying something else, but they will do exactly the same thing, right? And why is this going on? Like, why is it that models are so bad at learning from their failures? I think this is a little bit of a mystery, but I see this as being a very big gap. And I'm not sure right now how it's eventually going to be covered. My guess is that we are not really going to solve like this sample efficiency problem. What we're going to do is we're going to use our ability to like overwhelm the problem with greater resources to just scale past it. We're going to get the superhuman system that's just like we did in chess or Go and other domains, which is still less sample efficient, but because of the overall intensity of the resource inputs we're giving to it, is still more competent. But that does mean that you should expect us to get there to take like longer than you might otherwise expect.
Yep.
Okay, so let's take it for granted that we have AI that can do any remote job. Let's even go further and say that it can do like any physical job through robots, for example. What are the implications of this for the economy?
Yeah, so we've been thinking quite a bit about this, and one thing you might do is look at standard accounts of economic growth, and there are theories of economic growth, especially endogenous growth theory, that place idea generation and innovation as being very central to economic growth. So R&D and learning by doing, producing innovation, and this kind of economic theory tells you that what is important. An important fact about the economy is that there are increasing returns to scale. That is, if you double the inputs to your economy, capital and labor are the kind of key inputs, as well as resources that go into idea generation and innovation, then each doubling produces a greater than doubling of the outputs, right? So you double your inputs, your labor and capital, you can basically duplicate this kind of economic processes that you have set up. That gives you basically a doubling of output. And then you get this additional boost from innovation, making these processes more efficient, so getting more output per unit input. And so you have increasing returns to scale. And so, doublings of your inputs produce greater than doublings of output. Now,
actually, sorry, I'm confused about a point here. Like the main mechanism through which like the increasing returns to scale operate is through idea generation.
Well, so an important component is that you get every doubling of the capital and labor, say you get close to a doubling in output, but that there's this additional oomph on top of that that takes you to increasing returns. So it's the combination of the kind of returns to scale on the kind of accumulable inputs, which are capital and or these kind of two key inputs, and then on top of that, the returns to R&D. So those two things jointly determine the returns to scale of your economy. And so what this picture says is that if it becomes possible for each of your inputs to be something that you can invest into, so you can turn your output, dollars into more inputs, then you can get accelerating growth because you kind of double the inputs. That gives you a greater than doubling of outputs that you can then reinvest and kickstart this accelerating growth regime. Now, of course, we're not in that regime because the kind of a central input, labor, is not something that we can turn money into more labor. This is determined by population growth, which is somewhat independent of how much output, not quite, but it isn't determined exclusively by how much we're investing at the very least. And so
AI changes that.
AI changes that not because it changes human population growth, but it produces human substitutes that, for all intents and purposes, are flexible substitutes for human labor. And once you have that, then you can invest output into building more compute-related capital. So fabs, lithography machines, data centers, the energy infrastructure in order to power training and inference. And by virtue of that, you can kind of get a greater than doubling of output for every doubling of input, and you can reinvest this into the cycle that accelerates growth. And that.
So to paint the picture here, like we have this AI. This AI can like solve many tasks in the economy, can do many tasks in the economy. And one of the tasks that it can do is like it can also help produce more infrastructure for more AI. It can build help build more GPUs, which means that then you have more digital workers, more like instances of the AI that can do more and more tasks. And this is like the basic way that it's been accumulated. And like some of these digital workers are not only producing output, but also thinking about like how to make the whole process more efficient.
That's right. And so sometimes people say, this recursive, this kind of feedback loop of better technology, enabling you to produce better technology has always been around. So AI is no different. But AI is different in a very important respect, which is that AI promises to be able to flexibly substitute for human labor, such that there is no kind of bottleneck left that we rely on human population growth to try to unblock. And once you have that, then you get this kind of accelerating growth pattern.
But then you get blocked by other non-accumulable factors of production.
You do get blocked by those other factors. So those would be land or total kind of energy that you're able to harvest. Maybe there's some scarce inputs like kind of minerals or metals or rare earth metals. I think that is definitely something that eventually binds, but I think there's going to be a period of time when we have kind of produced the substitute for human labor, but we haven't yet kind of reached the kind of limits of how much output we can produce.
So the basic picture here is like right now, the binding non-accumulable factor is labor. Once that's lifted, there is going to be others, but like until we hit them, we can still have this regime of accelerating growth.
That's right.
Nice.
Yeah, so one way to maybe try to reason about when this might happen is when we turn something into an accumulative input and we accumulate tons of it, input like complementarity between different inputs is fairly strong, we're going to expect the share of that input in total gross domestic product to start to decline. And in fact, there's maybe some sign of this for labor, where like the labor share of output has been declining, though not particularly quickly. If you imagine that we completely commoditize labor in a you have tons of AI workers and they're very cheap, what's going to happen is the valuable things in the economy are going to become precisely those things we cannot scale, like land and energy and whatever. Those inputs are going to become very valuable. But you can just look at the rate at which the labor share has been declining. And that is not very fast, even though the economy has been growing quite fast and we have been scaling labor quite a bit. So if you just extrapolate, like how many more orders of magnitude of increase in labor could we get before like the other factors, according to current trends, are going to start to bite and like stop additional growth, there's like a lot more room. I think economists also would agree with this in the sense that if you ask them, like, are we likely to encounter like a decisive natural resource bottleneck or some other bottleneck to economic growth at present rates continuing for, say, 200 years, you're quite unlikely to get answers that are, no, that can't happen. We're going to hit some bottleneck. And all we're saying really is that AI is going to speed this process up because it's going to allow us to grow population much more quickly, which is going to allow everything else to grow much more quickly. And so we get to the point maybe we would get in 200 years instead in 10 years, 20 years of growth, something like that. And I like there's really, I think, no decisive arguments against this in the literature. Now, of course, implausible conclusion. Which I think makes people skeptical. And that's, I think, a totally fine thing. Like, you should be skeptical if someone comes along and tells you something totally unprecedented is going to happen over like the next 30 years. On its face, that's a very implausible claim.
We have been talking about how through this feedback loop of AI automating more of the economy, economic output being used to create more infrastructure for AI and idea creation, how this could result in like accelerating economic growth. I want to ask, like, do you see this as a given? What are like the uncertainties that one could have?
Yeah, so I guess we don't see it as a given. We have a paper that we published on the subject where we basically say if we define like much faster growth to be around 10x faster than what is typical in the world economy today.
30%.
Yeah, 30% per year. Then we say like if we get AI that is capable of saying what you did, what you said, basically, so doing what you said, substitute for humans not only on all the remote tasks, but also on all the physical tasks, then maybe it's like 50% that we would get like a 10x increase. So we are uncertain if that magnitude is possible or not. So there are arguments. Yeah. So right. So arguments in favor. Tamay already explained the most decisive argument, which is this idea about we get this increasing terms of scale, which is that we get more AI workers, we can reinvest ordinary kinds of physical capital, and we get a lot more researchers because AIs themselves can do research, which drives growth in what economists call total factor productivity, efficiency with which you use resources.
Also, learning by doing is like an important thing.
Yeah, I
besides
agree.
Like explicit science.
I would say that, yeah, I agree. There are other factors actually which contribute to the same kind of increase in terms of scale. Just the specialization of human workers is something in practice that contributes to it. Everyone learns a specific thing that they really are good at, and then they trade with each other, and that also gives rise to some amount of increasing terms of scale. But the general idea is this increases terms of scale. There are some other arguments, like even if you don't look at this, if you just look at what economists call factor accumulation. So we assume that there's no technological progress beyond what we've already seen, but we just keep reinvesting output into more chips and more robots and also more factories and whatever. Then the usual opinion in the growth economics profession was that this kind of thing can't really produce long-lasting growth. But I think the reason for that is that we are very used to an economy where labor cannot be accumulated. So once you remove that and labor itself becomes accumulable, then I think this conclusion that you just cannot get much more growth by just factor accumulation, that is overturned. At least we can get 100x, maybe 1,000x, I think, on top of what we have now. So that's an additional reason to believe this.
So one intuition for that is like, an H100 GPU costs like $30,000, and according to some estimates, at least, it does as much computation per second as, say, the human brain might. Although this is very uncertain. But it costs on the order of like $30,000, which is kind of lower than, say, the median wage in the US, especially among, say, like jobs that we expect AI systems to be disproportionately doing. So, at a rate of about a year, it'll be able to earn enough money to pay for another copy of itself. And so you get very quickly a doubling at the time scale of roughly a year. Of just pure factor accumulation. And so you get this very fast accumulation of these factors, which gives rise to very fast growth.
That's right. So I would say what is the decisive objection to really both of these views on some level is that, okay, there are some other objections like regulation. Maybe we're going to choose to slow down growth because we're worried about the risks, or just generically, we will prefer, we will be more comfortable if this transition happens slower. That's one possibility. But in terms of the physical possibility of it, as opposed to whether we choose to do it or not, I think the decisive objection there is really about these non-accumulable factors. We know these factors exist. Land is hard to accumulate, and physical space eventually can become a bottleneck. Energy is a limited factor that some other natural resources could be limited. And right now, these things, even if you sum all of them up, they don't account to a big fraction of the world economy. Most of the world economy, so first of all, the majority of it is just labor. And of the remaining parts, most of it is physical capital, both of which we assume will be accumulable in this world of AI. So we try to think about, okay, how much room do we have, even based on naive calculations, to just scale up GDP? Is it plausible that land or energy or rare minerals or whatever could be a bottleneck to growth? And I think we basically conclude that eventually yes, but this is many orders of magnitude away from where we are now. I think we've had an interesting experience talking to professional growth economists about this, because they tend to agree with this statement if AI is not in the picture. So if you just ask this question, like, can we keep up our just current rate of growth for like 200, 300 years? They tend to say, yeah, like it seems plausible. That's probably their default expectation. But if we then ask them, okay, like suppose we have this AI systems that can substitute for labor, we have these reasons to expect an acceleration, then can we get that same amount of growth, but in 20 years? And then I think a lot of them become a lot more skeptical. The reason I think is it's just intuitively feels very implausible. Like we're very used to a world of something like 3% per year growth worldwide. This rate of growth has been fairly stable since the end of the Second World War. And economists are just very used to think of growth as constant. Even the rest of us sort of take it implicitly, at least if people don't come from like a very poor country that happen to experience this very rapid catch-up growth, where they went from being very poor to something like advanced economy standards, then maybe they have a slightly different view. But generally, we think of this as being a fairly constant thing. And I think the basic heuristic there, that you should be skeptical if someone just comes along and tells you we're going to see this totally unprecedented acceleration in growth in the next 20, 30, whatever years, that this is plausible, you should be very skeptical. Similar claims have been made about other technology. People have said the same thing about the internet. People have said the same thing about, I don't know, nuclear reactors, nuclear power. Now some people say the same thing about fusion. And I think we would be skeptical of all of these claims because they don't really, like, labor is such a huge fraction of the economy. These other things are really not. Like, there's no reason to expect that increasing their supply by a lot would have such a huge impact on the economy. And we really do think, in this case, the arguments specifically about AI are very strong. Our best theories of economic growth just robustly predict this unless you make very unfavorable and like what look to us like unrealistic assumptions, which is why we think it's like there doesn't seem to be an obstacle to it being physically possible. Now, there is, of course, eventually we think we are going to hit these non-equal inputs, and then we're going to have some. So, for instance, people are worried about the impact of AI on wages and employment. This is something like people worry about a lot. And there is a common argument that is offered by economists as to why these worries are unfounded or overblown. And this has been offered also in past examples of automation. It's very simple. Humans always going to have some comparative advantage relative to AIs or other kinds of robots on some tasks relative to others. So the idea is we will always be able to gain from trading with them. We will not be worse off by trading with them. And the way this is manifested in the past is, say that cars become like much more efficient than like humans at transportation. We get on cars and there's no need to have horse drivers or horses, or like a lot of people can become unemployed suddenly. Or we have spreadsheet software, and then suddenly a lot of people whose job it was to multiply and add numbers in corporations, suddenly they're unemployed. But of course, unemployment doesn't stay out forever. Those people find some new task to do that is not yet automated. And in fact, the fact that these tasks got automated makes them more productive. So not only do their wages not go down, they in fact go up after they transfer to these new tasks. And I think economists have been looking at AI and just seeing it as more of the same. They're saying, well, it's just another kind of automation. It's just going to go the same way we've seen before. But I think the important difference is that AI is capable of substituting for humans across all of the tasks. And that is very different from doing it only on some tasks. One way to try to see what would happen is imagine that we have AI systems that can run on a GPU using, say, as much power as the humans use to survive. A human uses around 100 watts of power. And if it can take that amount of power and it can just deliver, like it can just do everything I can do, but like 10x better, then my wage will never be above like a tenth of what I need to even just stay alive, right? So there will be a big collapse in my wage, at least relative to the energy I need, and that's like wages falling below subsistence. So the reason the argument of economists about comparative advantage turns out to be not true is precisely because of the non-accumulable inputs they will point to when they object to the possibility of very fast growth. What happens is that we have so much labor that the value of labor goes down a lot. This doesn't mean humans as a whole are necessarily poorer, because humans can just own a lot of capital, a lot of land, a lot of natural resources, and the rents on those things in this future economy, we expect to go up a lot. So as a whole, humanity, at least if it keeps its current property possessions, is actually going to be much richer. It's just going to be that labor in particular is going to become much less valuable.
So the analogy here that this makes me think is aristocracy in like certain countries now, where like aristocracy used to own land. Because of that, they got certain resources, certain some resources that they have accumulated through generations, and there's like some historical wealth that comes through that. Like we might end up being like this in a similar position as like the aristocracy of the future, that because of our historical position and privileges, like we were able to accumulate like a lot of these capital and resources, that then like keep increasing in value. I guess that this also invites like this other possibility, which is that I believe that the trend is like for historical wealth to vanish, as like some members of some generations end up like gambling away their money, or like making some poor bets on like how they distribute their money, and like they tend to revert towards like not having like this special place in the economy. Like, are you worried about like something similar happening to humanity?
I would say it's very reasonable to expect that because, as you said, it's actually the base rate that like this kind of wealth that is built up does not last for that long. Like the wealthiest people in the world today are usually not the people who used to be the wealthiest. Like they're not the descendants of people who used to be the wealthiest 100 years ago. And it's actually a bit puzzling to explain that why can't they just keep their capital invested and keep getting high returns on it. I think there are a few reasons. So one reason is that wealth just gets divided as like one person is maybe wealthy, but they have a bunch of descendants, and their wealth just keeps getting divided through the generations. Mm-hmm. Another reason is if you just passively own wealth and you invest it, usually the returns you can get are less than if you combine the role of being an investor and also like a manager, a founder of a company. And so those people are able to get higher rates of return on their wealth, which means you might start from a higher base, but you grow more slowly compared to them. So they have the ability to overtake you. And this is definitely something to worry about in the case of an economy where AIs just do all of the jobs and humans are on the sidelines just living off the rents from their property. That can last for a very long time, but I would expect the AIs to eventually start to dominate the world economy in this sense, at least unless humans are able to take advantage of the large amounts of technological progress that will be made in this world to increase their own capabilities, to just not just remain on the sidelines.
Yeah, I think that this seems like pretty determined to me. As like economic time goes on, like I expect AI to be like a bigger fraction of the economy. Like whatever remaining a sliver of wealth humanity keeps is gonna be like a smaller fraction. I guess that there is like a crucial difference between it being like a small fraction, but still being like vastly more than we have now, and actually that shrinking to being zero, like leaving us in like a worst position in terms of wealth per capita we have now. Like, do you have intuitions about like which of these worlds are we headed towards?
I think if there is if we manage to retain like a peaceful economy in some way, and humans are not expropriated, then there's no reason to worry that humans as a whole are going to become much poorer. We own some wealth now. That wealth, I think, is going to have very high rates of return throughout the period of increased economic growth. So we will end up with a stock of wealth that is just worth an enormous amount by our current standards. I agree with you that over time, as a share of the entire economy's wealth, it is going to shrink. But the overall economy is going to be growing so much. Like, for instance, if you think about the effect I mentioned with founders getting a higher rate of return on their investments, well, they are able to do that because they are in the process creating a lot of value that was not there before. So yeah, they get a bunch of wealth, but that's because it's not because they have taken wealth that belonged to other people. It's because they have created a lot of new wealth. And that's would be my default expectation with AI. I also think that it is probably not reasonable to expect that with the amount of technological progress we can foresee, that humans are just going to stay on the sidelines forever, that the human capabilities are also not going to increase. At least, like if you consider the amount of wealth that would be available to some humans, at least in this world, there will be very strong incentives for the economy to offer products to them that can increase their capabilities, not just for reasons of productivity, but because that might, say, enable them to have much richer experiences. It might provide
prestige, and like you want to be on the side of like the very successful and prestigious types of beings.
Yeah. So like sometimes people wonder now, like say, like what would it be like to see like 4 colors instead of 3, right? And right now we can offer this experience to people, but in the future we might be able to. And there's a lot of things like this which people might well be willing to pay a lot for. I think a big one is really, the biggest one maybe is increase in life expectancy. Right now, this is just such a scarce good that no matter really how wealthy you are, there is very little you can do to spend your money to extend your life expectancy. But I think in the future, this probably will stop being the case. And if we need to, like in some ways, change something about humans to make them able to live much longer. Like right now, some of the problems is that like parts of your body that's just get worse over time. It degenerates, and we have no way of dealing with that.
How much are we gonna need to change in order to stay competitive with environment?
Right. So
because if I imagine myself like living like 1,000,000 years and like seeing 4 colors, like I don't think that gets me to like, oh, I'm gonna be able to compete with like an AI that can solve like math problems that Teritao cannot solve.
Well, we should get back to the scaling laws, right? Like we should think that the amount of power or wealth or whatever that's or amount of productivity that an agent is going to have in this economy should be roughly proportional to the amount of compute that they are able to use when running. As I think was mentioned earlier, the human brain does about as much computation, we think, as one H100 GPU. It's roughly similar. If you have a total of like billions or trillions of these GPUs, then, and there are some AI systems that run on millions of these GPUs at once. Well, obviously, I think it's very plausible that you're not going to be able to be competitive with those systems.
I think there are a bunch of interesting open questions that I'm excited for us to be working on. Yeah. So, one is this question of algorithmic progress and what really drives algorithmic progress. How is this downstream from, say, scaling, or is this something that you should think of as being largely independent from scaling of hardware? Is algorithmic progress mostly about reducing the costs of attaining already kind of achieved levels of capabilities of like training smaller models that are as capable as the large models that we just recently trained? Or are these algorithmic innovations around pushing out the boundaries of what our AI systems can do? Are these algorithmic progress, these gains in algorithmic, are these algorithmic innovations mostly in the form of kind of architectures and data quality, or other minor tweaks? Are they in post-training? And if so, exactly what is driving this? I think those are some questions that I'm excited for us to work on.
Yeah.
Other questions are, how fast are we going to get kind of these drop-in remote workers? I think this is a question that we can now already start to think about. Like our Claude 3.5 has this computer usability that it can kind of use your computer to accomplish some task. We are starting to see the kind of kindlings of drop-in remote workers, and we can try to study how fast are they improving on the tasks of the type that actual remote workers are performing. And then we can say something about scaling behavior. Suppose we increase the amount of compute by 10,000-fold, as we expect to happen by the end of decade. Will this be sufficient for automating 50% of work that basically we think the work that can be done remotely? What is the chronology of this automation? Which tasks are going to go first? And what is the pace of this automation? I think an important question is whether the pace of automation is faster than the pace of retraining. If that's the case, then I think this has really interesting qualitative kind of implications around wage inequality, that there are going to be there are going to be occupations that earn a lot because they have yet to be automated and are complemented by things that have been automated. But humans take too long to enter into those occupations because the timescale of training is so long. And so you might end up having a bunch of people who end up not being retrained to perform perform tasks. And as a result, you kind of get inefficiencies this way.
Nice. So I'd be curious again whether you have takes on either like what are like some key takeaways about AI that you think are important, or like also what is like some future work you're excited about?
Well, I mean, the key takeaway, I guess, if like someone is totally unfamiliar with AI, they come to listen to this conversation, I guess like the one sentence takeaway I would give is like the future is going to be here sooner than you think.
Yeah.
And I do think that's really important thing for people who are like not following this space to understand.
Like this has to be part of your lateral career plan, right?
Right. And Ege, you are maybe a bit more kind of skeptical of fast progress than many other people who we, even in our organization. So I think coming from you, this says quite a lot.
Yeah.
I mean, there's a big difference between people who are, I think, like tracking AI progress and people at labs or people who are outside labs, but sort of are sort of in the same social circle or something. Like they just have much more aggressive views about the rate of progress we're going to see over the next 50, 100 years. Some people even the next 10 years than the general population. I think the people just like do not expect anything like the rate of progress that we expect. Even economists, like telling an economist that you expect the rate of growth to like plausibly increase by 10x at least for a while in the next 30, 40 years, that's like a plausible thing that could happen. Like they are going to look at you like you're crazy.
We had dinner with a kind of development economist, and we were telling him about, we think it's plausible that we could get like a 10x increase in the growth rate. So 30% per year. And then he responded, oh, you mean 30% per decade? I'm like, no, per year. And you mean like 3% per year, right? No, 30% per year. And it took a while to get this through to him. But as soon as he like actually realized what we were telling him, he just started laughing and thought this was totally ridiculous. So there is this response that the economists have of this view as being pretty bonkers.
Yeah, and I would encourage people to like keep the like sort of very long run, like historical view in mind. We have seen a lot of things in history which are, you could even say, like more remarkable than what we're talking about here. You like, for instance, maybe really the most unlikely and still we don't really understand transition that happened is this transition of abiogenesis. Like you had planets with no life, and then suddenly it has life, and then suddenly you have these bacteria that can like multiply by 2 every 20 minutes, and then like they just like colonize the entire planet. It's actually like we take it for granted, but if you look like inside a cell, it looks like so complicated, and like that just like happened. Like it's just a thing that can happen. And then after that, even in human history, we went from the world population doubling like every 100,000 years in the foraging era to something like every 1,000 years after agriculture, to now the world economy is doubling every 20 years. So we have seen many orders of magnitude of acceleration and growth before. And this is one of the main reasons why so when people are skeptical, they say, well, in the last 70 years, growth has like been slowing down. Like what is how can you look at that and then say such a big acceleration is plausible? I would say, well, like you have to take a broader historical view. Like if growth has been fairly constant for like 70 years, okay, like maybe even if you know nothing about AI, you just come at it from a pure like trend extrapolation perspective, you could maybe say that's going to last like another 70 years, like 50% chance it lasts another 70 years. And like economists are, and also I think just ordinary people are just much more certain than that this like business as usual is going to continue. There are some interesting stories of similar views in the past. So for instance, before we entered the industrial era, progress was so slow that usually it was happening, but you didn't really see much progress in one lifetime. So people will sort of take it for granted that technological progress and new inventions and things like that, those are pretty rare. And in the 17th century, late 17th, early 18th century, people started to notice that that there was some real progress starting to happen in the economy. Like they could notice some changes in their own life. And this Isaac Newton said that this is very strange. We're suddenly seeing this progress. How could this happen? And his conclusion was that, it must have been because the civilization was destroyed before and we're just recovering, because he just couldn't imagine otherwise. He couldn't reconcile the rate of progress with why, if we can progress at this rate, why are we not already extremely advanced? He couldn't explain it. Now we think we have an explanation, this increasing terms of scale, growth stories, but I would just advise people to keep in mind that we have seen a lot of big changes. We're not saying something that is historically unprecedented in some sense. And that I think should make you less skeptical than you would otherwise be. That's really the main high level takeaway that I would want people to have. On the details, what specific projects that I think could shed more light on the future trajectory of AI, I think one concept, aside from, of course, everything that has been mentioned so far, that seems like it could be pretty important is this training inference compute trade-off.
Yeah.
This is important for several reasons. One of them is that it seems like it plays a pretty central role in your story about why synthetic data is such a plausible way to overcome data bottlenecks. And I agree with that view, but I do think this trade-off is just not super well understood. I think there's just a lot more work that we could do here. And the implications of this are, there's so many implications of this that I think we've realized over the past 6 months that it's really worth doing some more rigorous research in this area. I'm very excited about the possibility of just getting much better benchmarks that are actually going to be able to at least put up a fight against the enormous rate of progress that we expect. I think people are just not taking this very seriously in a lot of domains. They are just sort of building easy benchmarks that easily get saturated. I don't even know when GPQA is this benchmark that was created. It's a multiple choice benchmark. It was created by getting some experts and non-experts and then telling the experts, okay, write a question that an expert in the same field as you is going to be able to answer with a very high chance, but a non-expert, even with access to a search engine, is not going to be able to answer, again, with a high chance. But the resulting data set, in my opinion, was just it was not the kind of things that those experts are actually useful for in the real world. It was just things terminological things or formulas that those experts are expected to know, but are not very easy to find by Googling them. But a model that can do that, by in no means is even close to substituting for the experts that were actually part of that benchmark. So I think benchmarking efforts have been very poor. And we have, I think, already improved upon the state of the art in a big way in math. And I just think we could do much more of that. I just don't see the community paying too much attention to this problem. It seems like everyone wants these benchmarks to exist. When a new benchmark is released, everyone's yes, a new benchmark. It's so hard, it's so nice. But at the same time, when I look at how many people are working on creating such benchmarks, it seems so few.
Yeah. And in a sense, it feels like creating this benchmark is the obvious thing, right? If you want to measure how fast AI is improving, what you need to do is create settings in which you can evaluate this rigorously, which is what benchmarks are for.
For instance, in the case of GPQA, it was marketed as this very difficult benchmark. And then 1 year or maybe 1 year after its release, now models are already at 70%, 80% or something like that. Yeah. And So I think benchmarks are not created with the right framing in mind. They're people are maybe like stuck in the way of thinking about AI that was true like 10 years ago. They're stuck in let's create these like very narrow benchmarks. Let's test if a model can look at a picture and tell a dog apart from a cat. Like this was the kind of benchmark we used to have. And that's just like so primitive and so easy compared to what we need to test and probe for the capabilities that are going to lead to the big changes that we've talked about. So I'm like, maybe people are just not investing in this because they don't share our view of like how big the impacts are going to be. And in that case, I think we just have this like worldview advantage that we can exploit to build these like good benchmarks.
Yeah, I think our worldview on this is like fairly rich. We've thought about this quite a bit and understand, and I think have a better sense than a lot of people about precisely the way in which this automation might happen and the reason why this automation might result in accelerating technological change and economic change. And I think I want to spend a lot of time just harvesting that worldview and picking out things that we can translate into benchmarks so that we can understand, if you scale these resources like compute, data, so on, how much progress are we making on these tasks? And I think that will just inform us about how fast we're getting to this world that we expect eventually to reach.
Yeah, and I think that this has also put us in a much better position to advance the rest of our research agenda. Algorithmic progress, if we have more data on benchmarks, will be much easier to study. More generally, like this question of like, as you scale the systems, how much better they get, also are easier to study if you have this information.
And research about predictable evaluation. So suppose you scale up your model by, scale up your training compute and your data set and, maybe scale up the post-training and scale up inference compute. What exactly is the effect on benchmark performance or kind of real world utility? I think we will be able to develop a much more mature sense of this by investing in evaluations, by investing in good benchmarks. And I'm really excited to be making progress on that kind of research.
Yeah, this is the goal for us. Like, we want to be that organization that everyone can look up to for understanding how quickly AI is advancing, how quickly investments are growing, and how do you relate these two in order to think about where it might be headed. And we have done like a pretty good job here, but I think we're going to do like a much, much better job in the next year.
I would agree with that.
Okay, so we've been talking about many things today. We've talked about the mission of Epoch. We've talked about why we created this organization. We've talked about AI, how it has been able to achieve many incredible things in the last decade, in no small part due to like the incredible scale up in resources that the field has achieved. We expect this scale up to continue. We expect these improvements to continue and eventually have AI that can substitute humans first in remote work and later in like practically any kind of like economically useful task that you can think. And like if this worldview proves true, we also think that this will have dramatic implications on the economy, where like the economic growth might like drastically accelerate. Now, I think we need to take all these lessons very carefully and prepare for the future. And that goes through having accurate, up-to-date information on how fast are the trends of investment in AI and how fast are the trends of improvement in AI. And that's what Epoch AI is getting up to do. And I would love for the people watching here to like come with us in this journey, keep up with like the work that we're doing, because I think that by doing so, you're gonna end up being like much more informed about AI and the role that it's gonna play in our society.